So let's look at how the structure of an acid or base can relate to its strength. Okay, like kind of what makes a weak acid stronger or weaker? What makes an acid strong or weak? Okay, what makes a base strong or weak? Okay, and what makes a weak base a stronger weak base than another? Now the base stuff again is a little more sketchy or not quite as clear cut as the acid stuff. So what we're going to do though is the bottom line, if you think about it, the strength of the acid depends on how easy it is to ionize the hydrogen, right? We've learned HCl, HBr, HI, HNO3 fully dissociate, right? That means that 100% of the hydrogen breaks off. Okay? So those are what make them strong. So that must mean that their hydrogens are easily ionizable, right? But we know that the weaker acids, not all of the hydrogens ionize. In fact, like with HCN, only 7 in 100,000 ionize at a 0.1 molar concentration, right? So what is it about the structure of the acid that makes it strong or weak? Okay, so the first thing we're going to look at are what we call the binary acids. So acids that just have two different compounds in them, like HF, HCl, HBr, HI. In these guys, for this particular thing, if you're looking at hydrogen bonded to elements in the same group, like FCl, or and you start to run out of groups here, or you could say, well, H2O, H2S, H2SE, H2TE, it would have the same relationship, right? And NH3, PH3, ASH3, you could find this relationship, right? Which one would be the stronger acid? Okay, well, you look at the bond energy. And the bond energy, though, has to do with the relative size of the atoms, as you see in the graphic here. So below those, so looking at hydrogen bonded to all of the halogens, because this bond energy is weaker, and why is it weaker? It's because the intermolecular distance in HI is much greater than the intermolecular distance in HF, yes? Right? So it turns out HI is the strongest, HBr would be the next strongest, HCl is the next strongest, and all of those are considered strong acids. HF, though, is a weak acid. Why is it a weak acid? Well, because it has a high enough bond energy that it makes it harder for water to pull it apart. Because remember, to ionize, you have to have an ion dipole force from water that pulls that covalent bond apart. You know what I mean? So in this case, so that's HCl, HBr, HI are all strong acids, and actually HI is stronger than HCl. You predict that by structure. Now, how about if you go across a period? Well, for that, you're looking at electronegativity. And it turns out that HF, even though it's a weak acid, it's a much stronger acid than water, which we know only produces 1 × 10⁻⁷ hydronium, right? And ammonia is even a base. Ammonia is such a bad acid that it acts like a base, and CH4 doesn't act like anything at all. But where you look at here is the bond polarity. The more polar the bond, the more easily ionized the hydrogen. Because again, what happens is, remember, for fluorine, it's like 10 for me, 1 for you. 10 for me, 1 for you, right? Fluorine has the majority of the electron density. That hydrogen has hardly any electron density. And when a water molecule comes along, right, with a nice unshared pair, right, this hydrogen has hardly any electron density, and hydrogen's like, please, sir, but you have some more, right? In other words, I have hardly any electron density. Can I have some more, please? Right? And so that that makes that hydrogen more ionizable because it's craving some electrons that fluorine has stolen from it, basically, right? And so the more polar the bond, or the higher the hydrogen bonded, the more electronegative thing will make it a stronger weak acid. Okay. All right. Now you also know that you have this whole other category of acids where you have hydrogen bonded to a polyatomic ion. Okay? I'm going to pause it for a second. Okay, so now you have these oxoacids, which are acids where hydrogen is bonded to some polyatomic ion containing a non-metal atom like HOI, HOBr, HOCl, H2CO3. Again, you see the ionizable hydrogen is the hydrogen that's bonded to the polyatomic ion in this case. And so kind of going along with that same theme like we just talked about with HF, having that greater polarity and having that hydrogen have hardly any electron density and being more ionizable. The way oxoacids, what makes them stronger is to have a more ionizable hydrogen. Those are going to be the hydrogens that have the lowest electron density. Who are bonded, and what causes that? Being bonded to more electronegative atoms. Well, we already know that oxygen is electronegative, right? Well, what's that oxygen bonded to? Okay, so let's scroll down and see what happens if you have the same number of oxygens like you do in this example I have there with HOI, HBr, HOBr, and HCl. Okay, which one of those would be stronger? Well, whichever one of these is bonded to the more electronegative nonmetal, which is chlorine in this case, yes? Because not only is oxygen pulling all the hydrogen away from that hydrogen, chlorine has an electronegativity of 3.2. All right, it's more electronegative, you know that because it's farther over to the right, yes? And it's farther up than Br, okay? And then Br would be the next strongest weak acid, but HOI would be the least, okay? Because all those oxygens are pulling equally, kind of, taking the electron density from hydrogen, but in chlorine being the more electronegative atom bonded to oxygen makes this hydrogen say, "Please, sir, might I have some more electron density?" Right? Same idea as before, okay? So this would be the strongest of those three. So based on structure. And, they may, I've seen a question like this on the AP exam where they give you these three structures, right? They give you even the Kas. And if you look at the Kas of these, you would find that there is a gradation of Ka and HOCl is the highest. Ka, okay? They'll give you the Kas and they'll say, explain this based on the structure of the atom. Or structure of the molecule. And you would say, well, in HOCl has the higher Ka because it's a stronger acid. It is the stronger acid because chlorine is a more electronegative atom, which in addition to oxygen pulls a greater electron density away from the hydrogen, making that hydrogen more ionizable. Okay? Now this next part, I didn't get to finish writing in, and I didn't have, again, I didn't have my stylus, so we're going to try and write this in real quick. I know what I need to say here. So, okay, so what if you have the same Y? You have the same Y, but different numbers of oxygen, and you know what's going to happen here, right? The one with the more oxygen is going to be the more polar, right? Different number. I spelled that wrong, but okay. So that would be like HClO, HClO2, HClO3, and HClO4. Right? And so if you kind of think about this, is going to be like this. This is going to be HCl. I think it's like that. Okay, and actually it really doesn't matter double or single bond because what really matters is that you have, so this has an O and O and an O, and this would be the same thing, but this would have 4 O's bonded to it. Okay, remember chlorine can have an expanded octet. So there would be all these O's on there. Okay, well, just like we talked about before, the one that's going to have the most ionizable hydrogen is this hydrogen here, where, oh, it's actually, I did it the other way. There's an O in between here. I'm so sorry. You know what I mean, though. There's an O in here. I did it backwards. Okay, now that I've corrected the structures, let's go back and do this. So you can kind of see that this hydrogen of HCl and HClO4, right? Not only now you have 4 oxygens and a chlorine pulling electron density away from this hydrogen. HClO3, you have 3 oxygens, pulling even more electron density away, okay, or more electron density away. In HClO2, right, you have 2 oxygens pulling. HClO, you only have 1 oxygen in addition to the chlorine. So hopefully you can see pretty easily that this is the one that is going to, this hydrogen here will have the least electron density, and this one on this end will have the more electron density, more. It's not going to have a lot, but it's going to have more than the extra oxygen. So the extra oxygens act like, again, much more high electronegative atoms, causing the HClO4 hydrogen to say, please, sir, may I have some more electron density, that is. A water molecule comes around and it attaches to the water molecule, okay? And in fact, if you think about it, we said that HClO4 is considered a strong acid. This is pure chloric acid. HClO3 was that acid that's like the 7th strong acid because it has a Ka just above 1, right? But HClO2 and HClO are considered weak acids and they have a small Ka, okay? And HClO would have smaller Ka than HClO2, all right? So this is the relationship between for oxoacids. Bottom line is, the greater the electronegativity of the agglomeration of atoms bonded to the hydrogen, right? The greater that is, the more ionizable it is, and the stronger the acid will be. Okay? Okay. All right, gentlemen, I know we don't have a whole lot of time. Again, sorry about this, but we kind of got a front load. So what are some of the weak bases? Well, again, a weakly soluble hydroxide. The conjugate base of a weak acid will act as a base. But the ones that we want to talk about with how structure can relate to this are the nitrogen-containing bases. We know that you're a base. These nitrogen-containing bases are bases because this unshared pair in the nitrogen can accept a hydrogen, right? Okay? And so what would make a weak base stronger would be to have a greater ability to pull a hydrogen to it, okay? And in a sense, it looks like, and this is not quite as clear cut as with acids and bases. So which one of these guys would have an ability to pull electrons to it? It's basically anything that would give this nitrogen, right, this structure over here more electron density, okay? And then all these electrons, even with this stuff bonded to the nitrogen, would make this a more appealing set of unshared electrons. Again, it's not so clear cut. So as you can see, here's ammonia. This is called methyl amine. This is called dimethylamine. There's also a triethylamine. But you can see there's not a lot of change. But adding this CH3 group provides like this nitrogen, because what's this nitrogen going to do? It's kind of highly electronegative. It's pulling more electron density from these atoms over here in the CH3 group. Are you with me? So this nitrogen now is more electron rich because it has more things to pull electron density from, more atoms. So this nitrogen will be more appealing to a hydrogen that wants some more, right, electrons. Here, now you have 2 carbons and 6 more hydrogens that can provide some electron density to this nitrogen, which makes it more appealing to a hydrogen that wants some more, right? So with nitrogenous bases in general, what ends up happening, what if this carbon had an oxygen bonded to it? Well, again, that may take away from the ability of this nitrogen to pull, electrons to it. So there's a lot of different things that can happen, but the bottom line is, if you have a greater ability to pull a hydrogen to you, you're going to be a stronger base. And so it all depends on that nitrogen and what would give it greater electron density. Okay? So that's it.